Welcome to the fastest way to learn data structures and algorithms with this premium revision material. Today we are mastering LeetCode 139, the word break challenge. This is a classic dynamic programming problem that tests your ability to break down complex strings into smaller, manageable pieces. Given a string S and a dictionary of words worddict, we need to determine if S can be segmented into a space-separated sequence of one or more dictionary words. For example, if S is LeetCode and our dictionary contains Leet and code, the answer is true because we can split it into Leet and code. However, if S is cats and OG and the dictionary has cats, dog, sand, and, the answer is false because that trailing G leaves us stranded. Think of it like building a bridge across a wide river using prefabricated segments from a warehouse. The string S is the total span you need to cover. The dictionary worddict is your inventory of bridge pieces. You can only place a segment if its length perfectly matches a gap in the span and it exists in your inventory. If you can snap together pieces to reach the other side without any gaps or overlaps, you have successfully crossed the river. We will solve this using dynamic programming. We create a boolean array dp of size n+1, where n is the length of our string. dp index I will be true if the substring from the start up to index I can be segmented. We start with our base case, dp index 0 is true, because an empty string is technically segmented. Then, for every position I in the string, we look back at all previous positions j. If dp index j is true and the substring from j to I is in our dictionary, then dp index I becomes true. This lookback logic ensures we only build on top of substrings that are already valid. Let us trace this for S equals LeetCode in dictionary Leet, code. Our dp array has 9 slots, all initialized to false except for index 0. We start at index 1. Substring L. Not in dictionary. We move to index 4. When j is 0, the substring is Leet. That is in our dictionary. Since dp0 is true, dp4 becomes true. Now we skip ahead to index 8. We look back. When j is 4, dp4 is true. The substring from index 4 to 8 is code. That is also in our dictionary. Therefore, dp8 becomes true. Since we reached the end of the string with a true value, our final answer is true. In our Python code, we first convert the word dictionary into a set for lightning-fast lookups. We initialize our dp array with false values and set the first element to true. We use a nested loop. The outer loop I travels from 1 to n+1, representing our current target endpoint. The inner loop j checks every possible starting point before I. If dp index j is true, we extract the substring from j to I. If that substring exists in our word set, we mark dp index I as true and break the inner loop early. We have found a valid path to this point. Finally, we return dp index n. Looking at the complexity, the time complexity is O of n cubed. This is because we have 2 nested loops, and the substring slicing operation inside takes O of n time. The space complexity is O of n to store our dp array and the word set. And that is the word break challenge mastered. This subproblem approach is a powerhouse for string manipulation problems. If this helped you, hit that like button and subscribe to Leo Academy for more premium DSA guides. See you in the next one.